General properties. The transition metals show great similarities within a given period as well as within a given vertical group. Differences within transitional metals. Last electrons added are inner electrons, d electrons for the d block and f electrons for the lanthanides and actinides. Complex ions. Formed when you have small ions with large charges, they always create acidic solutions, two or more ions that act as a single entity, species where the transition metal ion is surrounded by a certain number of ligands. Ligands. Any molecule that binds specifically to a receptor site of another molecule, or ion, that behaves as Lewis bases. Paramagnetic. A term used to describe a substance that shows a relatively strong attraction to an external magnetic field. These substances have molecules containing one or more unpaired electrons. First-row transition metals. Scandium through zinc, representative of the other transition series, great practical significance. A set of orbitals with the same energy is said to be degenerate. In transitional metal ions, the 3d orbitals are blank in energy than the 4s orbitals. Lower. This means that the electrons remaining after the ion is formed occupy the 3d orbitals, since they are lower in energy. First-row transitional metal ions do not have 4s electron. Reducing agent. The electron donor in a redox reaction, the substance that reduces another substance by losing electrons. Oxidizing agent. The electron acceptor in a redox reaction, substance that releases oxygen. Lanthanide contraction. The decrease in atomic and ionic radii in the series of lanthanides as the atomic number increases, radii shrinks as charge increases. Coordinate compound. Bonds in which one atom donates both of the electrons necessary to form a sigma bond. This usually occurs between a transition metal with a high positive oxidation state and an atom containing a lone pair. NH3 bonded multiple times to a transition metal is probably the most common one you will see, e.g., Co4, trans metal ion with its attached ligands. Counterions. Anions are cations that balance the charge on the complex ion in a coordination compound. Oxidation state. Hash of the atom gains, loses when bonding. Coordination number. Reflects the number of bonds formed between the metal ion and the ligands in the complex ion. Coordinate covalent bond. Interaction between a Lewis base and a Lewis acid. Monodentate ligand, unidentate ligand. A ligand that can form one bond to a metal ion. Chelating ligands have more than one atom with a lone electron pair that can be used to bond to a metal ion. Bidentate ligand. A ligand that can form two bonds to a metal ion. Nomenclature. Naming system. Isomers. When two or more species have the same formula but different properties. Structural isomers. Where the isomers contain the same atoms but one or more bonds differ. Stereoisomerism. Where all the bonds in the isomers are the same, but the spatial arrangements of the atoms are different. Coordination isomerism. The composition of the complex ion varies. Linkage isomerism. The composition of the complex ion is the same, but the point of attachment of at least one of the ligands differs. Geometrical isomerism, or CI's transisomerism, occurs when atoms or groups of atoms can assume different positions around a rigid ring or bond. CI's equals next to each other, trans equals across. Optical isomerism. Isomers have opposite effects on plane polarized light. Chiral. Objects that have non-superimposable mirror images. Enantiomas. Non-superimposable mirror images which rotate plane polarized light in opposite directions and are thus optical isomers. The isomer that rotates the plane of light to the right, dextrorotatory. Isomer that rotates the plane to the left, levorotatory. Equal mixture of D and L equals racemic mixture. Crystal field model focuses on the energies of the d orbital, attempt to account for the colors and magnetic properties of complex ions, assumes that ligands can be approximated by negative point charges and that metal-ligand bonding is entirely ionic. Splitting of the 3d orbital energies. explains the color and magnetism of complex ions of the first-row transition metal ions. Strong field case. The splitting produced by the ligands, which is very large, electrons will pair in the lower energy T2 grams orbitals, greater than gives a diamagnetic complex. Weak field case. These will occupy all 5 orbitals before pairing occurs. Low spin case. Yields the minimum number of unpaired E's. High spin case. Maximum number of unpaired E's. Spectrochemical series. Ligands are arranged in order of decreasing change values toward a given metal ion. The magnitude of change for a given ligand blank as the charge on the metal ion increases. The ligand will draw closer to the metal ion because of the increased charge density. As the ligand moves closer, they cause greater splitting of the d orbitals and produce a larger value.